for linear feedback, shift registers, XOR, and that type of function, or it's instruction ledgers. The Pirate TV hackers will know why you want to find the instruction ledgers, but suffice it to say, if you knew what those are, you can read out the entire memory of even a secure chip usually. So we want to find a small set of ledgers. And of course, once we have the map, we'll just find 16 flip-flops that are close to each other and probably 2-3 areas where the instruction ledgers might be, and limit our focus to exactly those. Once we know what we want to target exactly, we'll run on those areas consistency checks. Our tools are not 100% accurate. They hopefully will be close to that soon, but we still want to make sure there's no errors. And errors don't go undetected usually, since they will lead to, they will violate some logic rules. For instance, that two outputs may never be connected to each other. That would be the most simple logic rule, because then they'll fight for the value, right? Simple rules like that. We run these checks, and once we're confident that the information we're looking at is actually consistent with all these rules, we'll inspect it. And that is pretty much a manual process, much like IDA Pro is at some stage, where we just compile different small blocks into bigger blocks and try to reassemble the algorithm as it was meant to be represented by the original designer. For instance, find the different building blocks of a cipher, which is the example I'll show in a second. So does that make sense as a process? So there's some manual work involved, as will always be with reverse engineering, since the computer will never know what's the most intuitive way of representing it to us. But most of the other steps in here will be automated at some point. Now, to do this manual inspection, we have a new tool too, thanks to Daniel Widekin and Stefan Skillen. This is just a viewer tool, really, that helps us tremendously in moving around the circuit, drawing boxes, grouping things eventually, and just having a much more intuitive way of interfacing with this netlist data, which, as it comes out of the DGATE, is just a large XML file. So this helped us very much already. The way we've been hacking chips so far is with pen and paper, really. This is some part of the Legic RFID chip. And once Starbuck was done with tracing all these wires in the DGATE tool, he came over. And how long did we take to draw this out? Maybe an hour? 2 hours, yeah. 2 hours at most, maybe. I would say an hour plus an hour of drinking coffee. So that's how long it takes then to find a cryptographic function. Granted, this is a very small cryptographic function, but one afternoon should definitely suffice once you have the information in the DGATE. And then it took me another hour to convert it into this beautiful PowerPoint representation. Well, so if you count the boxes, there isn't very many. Each of those is one bit of state. Clearly, this is insufficient state for any security primitive. So we hereby declare Legic Prime RFID tags to be completely insecure from a cryptographic point of view. After running DGATE for some time and sitting down for an hour documenting what this tag does. As further motivation why you should get involved, we did look at a bunch of chips and found all of them to be interesting from a cryptographic point of view, some of them to be severely flawed. Some of you might have heard of the MIFARE and how it's not all that secure. The Legic Prime is another instance. We had a talk this morning about the NXP high-tech RFID tag. That's not secure at all. There's others that are slightly better, like what we use in cordless phones, the DECT phones, or what some payment cards in the States use these days, but it's still not cryptographically sound from an academically point of view, I would say. So there's huge interests by cryptographers to look at these ciphers and to figure out whether or not they're secure. And we mostly just want to enable them to do these analyses. And it has been a lot of fun doing this, and I would hope some of you will want to get involved too. So this list on the last slide was fairly short. There's bunches of other proprietary systems that yet need to be documented, and we feel like there's definitely enough fun and publicity in it for a lot of you to want to jump at this. We know that everything that's kept secret, as in cryptography, proprietary, is usually weak or tends to be weak. So help the cryptographers get at this data. We would eventually want to see, of course, for microchips that we are asked to trust, as in a trusted platform module, to go through an analysis like this. So far, all these chips with the security certificates do not experience a high level of reverse engineering. There's very small sections of reverse engineering in the common criteria standard, but it's mostly intrusive fault injection or side channel attacks. We will want reverse engineering to become more common again in the design of microcontrollers, to point out design flaws like the ones we found early on in the chips we are asked to trust, right? And with that, I think I saw a 10-minute flag, so we definitely have plenty of time for discussion if there's any questions. Oh, well, just a quick heads up. If you do want to get involved, not just in hacking your own chips, but actually help us make this process even more streamlined, there's plenty of work, especially for programmers. Extending dgate, further automating things, extending it perhaps to your custom designed Amiga chip from the 80s. We get requests like this all the time. So there's different domains of chips that we can't break yet because they're just way too old. And people, in fact, don't want to break them really. They just want them to be documented somewhere. Beyond programming, we could also need some mechanical help. Turns out that the most expensive piece of equipment is a little stepper, a little XY stepper to put under the microscope. It's ridiculously expensive compared to the whole microscope. So if anybody has an idea of how to create one cheaply, like the RepRap, but maybe an order of magnitude finer.
I have a quite simple idea. Just take an old hard disk, you have a linear drive, and then you have one. Take an old hard drive, then you have a linear drive, and if you apply DC to the coil, it moves in one or the other direction, okay. and then you should get some position, and so you can make a mirror and maybe some CCD scanner line, and then you know where it's moving, and so this would be one construction. So you can move a lever from left to right, and so you make this 2 times, and so you have an XY drive that is a little bit. It has cylindrical coordinates, so you have to be a little bit calculus, but it's a cheap solution.
Yeah, it should work, but we need a really low resolution, so about some microns.
But the hard disk.
A hard drive makes this. Have you seen a 50 gigabyte hard disk? It has a very fine resolution.
Okay.
Because a voice coil has an indefinitely fine resolution.
Well, the idea of using a hard disk came up before in this context for the polishing, to use the rotating surface to polish your chip. So we can take apart the hard disk and recycle every part of it.
This was invented before. Go to Antwerp, look at the diamond grinding machines. They look like this.
Exactly, yeah. Thanks for the idea. We'll definitely look into this. So yes, please get involved on the programming side or with ideas like these. We definitely want to extend this to more domains. And with that, finally, I want to thank you. Send us questions by email, download the tools if you're interested, or ask questions now. Thank you very much.
Thanks.
Should we give people a chance to ask questions?